In the last video, we just learned how to build a recurrent neural network with the use of TensorFlow carriers. But so far, we haven't touched on the pitfalls about the recurrent neural network and what kind of problems that practitioners face when building these types of neural network. In this video, we will explain one of the key problems when training recurrent neural network and how we can solve them. Let's go ahead and get started. One of the problems with training recurrent neural network, especially very deep neural network, is the vanishing gradients and also exploding gradients problems. It's mainly because the slopes can sometimes be very big or very small, and this makes the trainings pretty difficult. Let's assume that we have a very deep neural network as shown here. For the sake of simplicity, we just assume each layer has only 2 hidden units, and each layer has linear activation functions, where G here is the linear activation functions, so the input is actually equals to the output. And at the same time, let's assume the bias parameters is ignored, and that is equals to 0. In this case, we have these following output equations. That is, the input is after the activation functions, that is equals to the outputs. So let's take a look on this example. Say we have an input X that is shown here, and then after going through the W1, W1, W2, W2, W3, and so, until the last one, Wn, it will give you the output Y. And here we can actually convert W1x into a Z1 because the W1x is equals to C1, and then this Z1 is actually the output for the next layer. However, because the activation function is a linear activation functions, at the same time, we do not have the bias parameters. Therefore, after the activation functions, the Z1 is actually equals to the hidden layers outputs, that is the A1. So we can just simplify this W1x equals to Z1. And then so on, we can just simplify that this W2 times the Z1 equals to the Z2. Because everything's because the activation function is linear, and at the same time the bias is ignored. And technically, the last weight parameters is a little bit different in terms of the dimensions. This mainly because the outputs sometimes that you have to match with the applications or match with your purpose. Now let's say each of the weight parameters, weight matrix here, except the last weight parameters that is larger than an identity matrix a little bit. Now let's say that all of them are equals to 1.5, 1.5 instead of equals to an identity matrix that is 1, 1 here. And then if we just combine everything all together, the output equations will be the y hat, that is your output. That is the Wn. Wn is a little bit different in terms of the dimensions. We just try to ignore that. And then that will times the identity matrix, which is a little bit larger than the identity matrix. That is 1.5, 1.5 here. And then that is the last layer with the input values x. And therefore, for a very deep neural network, you could imagine that n tends to be a very, very large numbers. As a result, output as well as the gradients here explode. On the other hand, let's say each of the weight matrix here is less than an identity matrix that is 0.5, 0.5 right here. And similarly, we have the output equations, but for these times, it will change from the 1.5 to a 0.5 and 0.5. And for a very deep neural network, and n tends to be a very large numbers, in that case, outputs as well as the gradients will vanish. For the vanishing gradients problems, the deeper the networks, the lower the value of the gradient is. and therefore the harder it is to train the weight, which is often the main issues to be used when we are using the recurrent neural network. Here are some solutions to the vanishing and exploding gradients of the recurrent neural network. For exploding gradients, the following methods can be used. Say, for example, we can truncate the back propagations. So, for example, we can stop the propagations after a certain times, and we try to limit the number of the layers or number of the steps. At the same time, we can set a penalties to try to reduce the gradients, or we can just clip off the gradients or putting a maximum limit on each of the gradients. For the vanishing gradients problems, there are some methods, of course, we can also use to try to solve that problem. Say, for example, we can initialize the weight. We can artificially initialize the weight so that the potential for vanishing gradients problems is reduced. At the same time, we can use a specified network called the echo states. On the other hand, we can also have a specified network to solve the problems that is so-called long short-term memories. For the echo states network, please feel free to find the details in this notebook. In here, I already provide you the link. However, because this is a little bit beyond the scope of this specialization course, so I will skip this. The most commonly used approach nowadays is so-called long short-term memories, and that is how to apply this long short-term memories network to solve these vanishing gradients problems. Let's dive into it in the next video.